Right, hello. We're starting chapter 10. I'm going to start with a recap on probability from GCSE. I'm not going to go into too much detail and I'm going to try to do it relatively quickly. I'll start with some of the basic language. So probability has quite a few key terminology in it. You need to be aware of quite a few words mean, and unfortunately you are going to have to learn what some words mean and then what the formula would be for that particular word. In any case, we're going to start with the very basics. So when we talk about probability, we're talking about first of all some experiment that is going to occur. Now I'm not talking about a scientific experiment. I mean, I could be, but I'm actually on about just basically anything where you can observe some outcome. So you could flip a coin and maybe it comes up heads, maybe it comes up tails. You can watch a football match and maybe the home team win or the away team win, or it's a draw. You know, there's lots of things, lots of examples. And beforehand, you might express some interest in an event occurring as part of this experiment. So, you know, for example, rolling a dice, you might say, oh, I wonder if it's going to come up an odd number. So technically what an event is it's a set of outcomes. So we actually use set notation. So this is with these sort of curly brackets, and you list the elements of the set inside with commas separating them. So if you need to revise your set theory stuff from GCSE, you know, things like union and intersection and the is an element of, and you know, your Venn diagram stuff, because that is actually what this part of the book, section 10.1, is actually pretty much going to be about. So you need to be confident with that stuff from GCSE. So anyway, technically an event is a set of outcomes. Now in the book it talks about it being a group of different outcomes from within the sample space, but it's really on about the same thing. So anyway, a trial of the experiment occurs, so that means the experiment, we actually run it. Maybe it's something that we could repeat many times. For example, we could roll a dice many times, we could flip a coin many times, but there's only one attempt at this particular football match, for example. There's only, you know, if I say what's the probability that what day could I say? Friday the 26th of February. What's the probability that on Friday the 26th of February 2021 in the northeast of England it snows? Okay, so if you're watching this video before that date, there is some, you know, it's an unknown, isn't it? It could happen, and it's probably unlikely, of course, but it could happen, and so there's some probability associated with it. But it's not an experiment we get to run again, is it? So, you know, there's sometimes the number of trials is actually fixed, right? We can't just keep repeating it. But in any case, we'd observe an outcome, and this is also said that the outcome has been realized. And if the outcome was favourable to the event you were on about, then you would claim that the event had occurred. So here's just a really simple example. So the experiment might be that we roll a dice. It's pretty standard. We might be interested in getting an even number. So this is the set that we'd be on about in terms of this event. Okay, so the different outcomes that would, you know, if we got a 2, we'd say yes, we got an even number. If we got a 4, we'd say yes. And if we got a 6, we'd say yes, right? So these are the different outcomes that are actually favourable to the event A. And therefore, those are the outcomes that actually make up the set that is technically the set, which is what A is. Okay, so then we roll the dice. So that's us doing a trial of the experiment, and we see we got a 4. So a 4 was observed, and since 4 is an element of the set A, so this is the symbol for being an element of, or being a member of, we would say that the outcome was favourable to A, and therefore that the event A occurred. So A gets a big tick, it happened, right? So for a given experiment, you've got lots of possible events, and any event that you want to put forward has some associated probability of occurring. So of course this is a measure of how likely it is. So probabilities are of course between 0 and 1, where 0 means impossible and 1 means certain. We're going to write the probability of an event. Instead of long-winded with all those words, we're just going to write P brackets A, so P of A, the probability of A occurring, and that's going to be somewhere between 0 and 1. Could be 0, in which case A is impossible, can't happen, and or could be 1, which means it's certain to happen. So for example, roll a normal dice, an ordinary dice, and I could say, okay, what's the event getting a 10? It's like, well, it's not possible, is it? So the probability of that is 0. This is like a GCSE question. So I might actually, at this point, ask you to pause the video, read the question, and have a go. And see if you can remember what to do. I'll give you a couple of seconds. Right, well done if you've had a go. Let's have a look at the answer. So we've got, so you draw a probability tree. So you'd have the first counter, you'd have the second counter, and we've either got red or green, red or green, red or green. And here I'm going to write probability of red, here I'm going to write probability of green. Now I'm doing this not because it's obviously the most efficient thing to do. I know I could put the probability straight on, but it's because I'm going to be introducing something that you are actually already aware of, but you've not ever seen it really written like this. So the first counter being red has some probability of it, so probability of red on the first go. Now, what would I actually write here? I'd have to put the probability of red given that it was red on the first go, and this is the probability of green given that it was red on the first go. This is the probability of red given that it was green on the first go, and this is the probability of green given that it was green on the first go. So if I actually fill some of these probabilities in, so the probability of red is 3/7, and the probability of green is 4/7. But now there's a counter out of the bag, right? So this probability here is actually a conditional probability, because we know that there's a red counter that's now gone out of the bag, which means there are only 2 left, and there are only 6 counters left. So this is actually a conditional probability. Right, it's a conditional probability. It's conditional on what came before it. So this would be, of course, 4/6. This would be 3/6, and this would be 3/6. Because in this situation, we've only got 3 greens left because we took one out if we followed this path. And then, okay, if you remember what you're supposed to do, you're supposed to multiply along the branches. So you'd have the probability of a red and then a red. Is 3/7 times 2/6, which is 6/42, which you can simplify, but you don't have to. So it's really important to notice that this is an and, right? We have both of these things at the same time. We've got a red and we've got another red. So I will come back to that because it's going to be very relevant that you remember that you multiply along the branches of a probability tree, and you are actually, these probabilities here are conditional probabilities. Okay, you have to be aware of the previous path you took to work out the numbers that you put on here. Okay, because it matters, it depends on what came before it. Right, these numbers here are different to these numbers here. Right, So you want to put a little title, probability formulas, and you want to put a little reminder that the union symbol means or, and the intersection symbol means and. And in terms of the shading in on a Venn diagram, or is this whole thing here. So that's that. So that's A union B, which is A or B. And then for the and, it's just the bit in the middle. It's both of them simultaneously. It's both of them at the same time. A is true and B is true. So this is A intersect B, which is also the same thing as saying A and B. And so we're going to do our first formula. It's called the OR formula. So you're going to need to write this title, and we're going to have two events, A and B. And what we want is we want a formula for the probability of A or B. So this is what the goal is. And so this is what we're about to do. So you will draw yourself a little Venn diagram that looks like this. And perhaps in one color, because what I'll do is I'll go through it. But what you might want to do is you might want to, for the bit in blue, so there's going to be some blue and some yellow that appear in just a second. But for the bit in blue, you might do lines going like this. For the bit in yellow, you might do lines going like this, just in case you don't have colors. So anyway, what you're going to start by doing is you're going to have the probability of A or B, which by the way is somehow we want to get a measure of what's going on inside these two circles. So I'm going to have the probability of A, and I'm going to add to it the probability of B. But there's a problem. And if you were in class, I would ask you what's the problem? Like, this isn't quite right. At the moment, this isn't quite right. There's a problem. Okay? So there's going to be something that we do to this. What's the problem with this formula? So let me show you again what we've done. We've got the probability of A, and then to that we have added the probability of B. Now the clue I will give, in case you haven't managed to get it, is that this is actually a little bit too big because we've added a bit much. The problem is actually in the middle here. We actually need to take away one copy of the middle part because we've double counted it. We've counted it once for the probability of A, and then twice, which is too many times because we just want to count it once. We want this part, and this part just once, but we've got the middle part twice because we've got it included here and here. It overlaps. We actually want it just once. So we have to take one copy of the middle part away. Now the middle part is the AND bit. It's the intersection. So this is the formula. You see, if I take away one copy of the middle and actually get rid of it, I've actually perfectly got exactly what I want. Yeah, or I could have taken it away from the other bit. Right. In either case, I am getting rid of one copy of the middle bit. And so this is your OR formula. Very, very important. Very important formula. And you need to remember this formula, and you need to be able to explain where the formula comes from. So I'll just very briefly recap what we just did. We added the probability of A to the probability of B. But because A and B, it might be possible for them to happen at the same time, we would have actually wrongly got too much going on in the middle here because we've included it in A and also in B. So that's the problem. So what we do to make up for that is we actually just take away one copy of it. and then we're left with the right formula, right? Because it's basically it's out, it's popped, and we've got the right formula. Okay, or over here I've got it like this. Anyway, that's your formula. You need to know it, and you need to be able to explain it as well. Okay, so that's the OR formula. And then there is some key terminology for some special situations. So there's 3 key bits of terminology. The first one is what it means for A and B to be exhaustive events. So you might want to write this down. A and B might be exhaustive events. This means at least one of them is certain to occur. It could be that A occurs or B occurs, or maybe both of them at the same time. One of those will always happen if A and B are exhaustive. At least one of them is certainly going to occur. So it's kind of hard to get the logic right. It's not saying that either A is certain or B is certain. It's saying that sometimes we might get A, and maybe sometimes at the same time we might get B. But if we don't get A, then we will get B. And if we don't get B, then we would have definitely gotten A. So for example, a Venn diagram that could look like this. So this would be exhaustive. This would be an example of exhaustive. So maybe I've got 0.3, 0.2, oh, I should have drawn this a bit bigger. So 0.3, 0.2, 0.5. Okay, A occurs with probability 0.5. So only half of the time A happens. So that's not A being certain by itself. And 70%, so 0.7, 70% of the time B will happen. 20% of the time, both of them will happen at the same time. But do you see how these probabilities all add up to 1? The probability that will go here is actually 0, right? Because I can't fit any more probability into this sample space, into this Venn diagram. So what this means is that A or B, this part, we're guaranteed to be in this part of the Venn diagram. Guaranteed. And so that's what it means for A and B to be exhaustive events. It's certain that at least one of them will occur on any given trial. Okay, individually, they might not be certain. Okay, A is not certain, neither is B, but at least one of them occurring is a certainty. Because say A doesn't happen, say we know that A doesn't happen, then B must happen. And if B doesn't happen, then A must happen. Because all of the probability is inside this part of the Venn diagram. So this is what it means for A to be exhaustive. So it's really important that you get that clear in your head, that you make these good notes, that you might draw a little picture that looks like this, just to illustrate the fact that it just basically means that all of the probability is contained inside the A union B part of the Venn diagram. Okay, in that situation, A and B are exhaustive. And it's actually quite a straightforward formula, actually. It is just this formula. That the probability that either A or B occurs is 1. It's certain. Okay. Another one, so the second thing is that A and B might be mutually exclusive. So you've probably heard of this one. You might not have heard of exhaustive, but you've probably heard of mutually exclusive. So this is a special situation where it would mean that A and B, it's impossible for them to happen at the same time. So one formula for that. So there's two equivalent things you can write down. The most common one to write down is just that the probability of A and B, remember that's the middle, and is the middle, would be 0. Okay, so the probability of A and B would be 0. So if I just draw a really small little Venn diagram here, it would mean I'd have 0 in the middle. Okay, very, very small Venn diagram. It just means that there's no probability in the intersection. Okay, it's impossible for them to occur at the same time. So if you think about what that would do to the OR formula if we were mutually exclusive, what that would do to the OR formula would be that this bit here would just be 0, because the probability of A and B would be 0, so it would be minus 0, it just wouldn't be there, which is why it would kind of simplify it to this formula here. So this formula here is a special case of the general OR formula for when A and B are mutually exclusive. Okay, it basically just gets rid of this bit here, because that bit there is just 0 if A and B are mutually exclusive. Right, and before I talk about the last one, I will just make this point that you'll want to pause and you'll want to have a think, because I'm probably presenting all of this quite quickly. There is a pause button, there is a rewind button. You can pause, take a break, come back. This video is supposed to just contain all of the information, and it's kind of up to you how you access that and digest that information. So anyway, what would it mean to be both exhaustive and mutually exclusive? Because it's possible to be exhaustive but not mutually exclusive. I mean, here's a picture. These are exhaustive events, but they're not mutually exclusive. It's also possible to be mutually exclusive but not to be exhaustive. It would just mean that there's a 0 here, and this might say 0.2, and then there you go. There's a picture for that. If we are both exhaustive and mutually exclusive, then, well, first of all, this probability of A or B, since we're exhaustive, this would equal 1, because the probability of A or B equals 1 if we are exhaustive. And also, because we're mutually exclusive, this bit would be 0. So what that would mean is that the P of A plus the P of B part would equal to 1. So yeah, quite a nice little formula for if A and B are exhaustive and mutually exclusive. Okay, so just a reminder, this would mean that the probability of A or B would be 1. This would mean that the probability of A and B would be 0. And if we take our general formula, which is this, so we add the probability of A with the probability of B, but we take away one copy of the middle because it's basically being double counted. And basically we just do a substitution, right? If we're exhaustive, then this part here is 1, and if we're mutually exclusive, then this part here is 0. So you end up with the formula that I've written there. Okay, the last special situation is if A and B are independent events. But in order to discuss what that means, and I'm sure you can probably remember what it means from GCSE, I do need to talk a little bit about what we were doing before, which was this probability tree stuff and these conditional probabilities. So basically I'm going to try to explain or try to justify why we multiply across in a probability tree. Okay, why do we multiply across? And because, why do we add up at the end? Because I've actually answered this now. Why do we add up at the end? It's because right at the end, all of these things, it's this, or it's this, or it's this, or it's this. And since all of these pathways can't happen at the same time, they're all mutually exclusive, You just add the probabilities at the end. That's by direct consequence of that OR formula. But what I need to show you is, why do we multiply across in a probability tree? So that's what we're going to do now. Okay, so this is kind of the idea from a probability tree, right? We have A, and this is like B given A, right? So, you know, here's your probability tree, dot, 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 dot. There's a bunch of other things in the tree, but we might just be interested in this branch and this branch. So we want the event A to happen, and then following that we want B to happen, and we might need to take into account the fact that we know that A has happened, right? Because it could affect the probability of B. It could make it more likely, or it could make it less likely. And so really I literally have probability of A, probability of B given A, and this right at the end would be the probability of A and B, which is this product. Now I should just say, this straight line is just shorthand for the word given in this context. So I might start writing that when I'm trying to be quick. So I'm going to try to justify where this formula comes from. Well, let's first of all consider the probability of B given A, which, as I just said, uses this straight line instead of the word given, just to save a bit of time. So the probability of B given A, well, given A has happened, we know we're in this circle, we're in the A situation. We're actually zooming in on A. So it's like, let me just do this. So this is like the given A, right? You zoom in on it, right? You basically don't care about anything else, right? You just don't care about it because you know A has happened, which kind of makes this part here your new sample space. A has happened, so you know you're in the A circle. Now we want to ask, okay, we know A's happened. What's now the probability that B is going to happen? So that would mean we would have to be in this part, right? Because this is the bit that has overlap with B. This is the part of A. This green bit is the bit that we'd want to be in, right? And it's this out of this. It's this out of this. If this is very small in comparison to this, then the probability of B, given that we're in A, would be quite small. If this was quite large, then we would say the probability of B given A was quite large. This, it's basically saying, look, it's this green part out of the red A circle, right? So this is what I'm trying to say. Let's really consider what the formula is asking. We know that A has happened, so we've zoomed in onto A. We now want to ask, okay, what's the probability of B then, given that A has happened? So this is not the same thing as the probability of B by itself. B by itself, we don't know if A has happened. Maybe it has, maybe it hasn't. It would be just the entire B circle, actually, for that. This green part is the part of the B circle which is still around after we know that A has happened, after we zoom in on A and ignore the rest of the Venn diagram. And so if I want to know what the probability of B is given that A has happened, I should be interested in this part out of the circle, out of the A, because it's a proportion. But this green part actually has, well, we know what this is. This is the probability of A and B. It's the middle part, isn't it? And we actually know what the red circle is as well. It's the it's A. So the probability of B given A is the probability of A and B out of the probability of A. Now I'm hopeful that I've explained that relatively acceptably. I mean, I'll show you an example. I'll show you an example. So perhaps we have 0.3, 0.2, 0.4, and 0.1. Now, if I ask you what's the probability of B, that's 0.6. If I ask you what's the probability of A, that's 0.5. If I ask you what's the probability of A and B, that's 0.2. What about the probability of B given A? So what that would mean is we've zoomed in on the A, and this could have been a question at GCSE, by the way. What I'm doing right now is not specifically A level. You would think, okay, it's 0.2 out of 0.5. So what's that? 2/5, which is 0.4. So it's 0.2 out of 0.5. Right, if you think about it, if you know A has happened, B has now become a little bit less likely to have happened. And you can see that with the change in probability. So anyway, if you rearrange this this formula here, this is kind of where you just rearrange this formula times by the probability of A, both sides, and you get the formula that we were just talking about. The probability of A and B is multiply up by the probability of A and then this is exactly it. This is telling you to multiply along the branches of a probability tree. Now, that part there about the conditional probability in this formula is quite tricky. If you haven't fully followed that, don't worry. You can ask me about it when we're back in school, and I can try to give you more concrete examples. I don't want to make the video too long. It's already probably really long. So I can't do this loads and I can't go on and on and on about it, but this is basic. This is how to show it. I can certainly go through it again at school. So anyway, that's the AND formula. Maybe I should say this, right? We've got and there's the OR formula. So we need to say what the AND formula is. The AND formula is this. That's the AND formula. Okay, and all it's really telling you to do is you want A, you want B given A. It's just telling you whatever goes here, you multiply along a probability tree, right? It's just telling you to multiply along the branches. That's all it's actually telling you to do. Okay, the AND formula tells you to multiply along the branches. The OR formula tells you to add up at the end. That's the basics of it. So okay, what does independent mean? So this is this last bit of key terminology. It means that if A has happened, then the probability of B doesn't change. It stays the same value as before we knew A had happened. And equivalently, if we know that B has happened, then the probability of A doesn't change. It's still as likely as it was before we knew that B had happened. So in, a practical sense, that means A doesn't have any impact on B, and it means that B does not have any impact on A. So very obvious sort of straightforward examples that you'll be hopefully well aware of from GCSE are things like, flipping a coin and rolling a dice, right? If I flip a coin, get a heads, does it affect the probability of getting a 5 when I roll a dice? No. Okay, these two things are independent. Which means, because of the AND formula, which of course, if you think about it, it's just this part here to begin with. That's the general formula. But if B given A, if this part here, if knowing about A, knowing that we got heads, doesn't affect the probability of B at all, it's still just the probability of B, we don't care that A has happened, just tells you to multiply the probabilities together. So it would be, a half times a sixth, be a 12th. So, yeah, you've got this for independent events, right? It's something to do with AND, okay? So really key is, so mutually exclusive and exhaustive, that's all to do with OR. That's all to do with the union in the Venn diagram. Independent is all to do with AND. And basically it's a massive simplification of the AND formula. Where you just multiply the two probabilities kind of separately and you just multiply them together. Now, I know I just said that mutually exclusive is an OR thing. Okay, it is also kind of an AND thing as well, right? Because it's the probability of A and B would have to equal 0. But I guess it is also kind of an OR thing as well, because it's just you add up the two probabilities. So yeah, if I was to try to summarize that, by the way, I would say that OR is all to do with adding, and is all to do with timesing. And if you're mutually exclusive, it's just the probability of A plus the probability of B. And if you are independent, then it's the probability of A times the probability of B. Now, unfortunately, yes, you're going to have to reach a stage where all of this kind of becomes second nature to you. So yeah, there's some work to do, isn't there? So I'm going to summarize it now for you. So you might screenshot this and print it out, or you might write it out neatly for your own notes. It's up to you. So probability formulas summary. So I've given you 3 sentences here. So the probability of B given A, which is written like this. So it's a straight vertical line going down. Basically, it's the updated probability of B happening given that we know that A has occurred. The probability of A and B is the probability of both events A and B occurring at the same time. Probability A or B is the probability of either event A or event B occurring, or perhaps both. So remember, for AND, it's just this. So that one's AND. And for OR, it's... Oops. Let me start again. Kind of hard to do this. There you go. It's this. That's OR. So these things are different. Right, so here are your general formulas. So you got the OR formula, and these are always true, by the way. These are always true no matter what. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. You need to have some understanding of where this formula comes from. So it's because we're adding the two circles together and realizing we've got too much of the middle. So you take one copy of the middle away. The second formula, you'll get away at AS level for sure, not being able to give a good explanation on where this formula comes from. It is far more complicated than this. This crops up far more in year 13 rather than year 12. I'm just including it here because I want this video to basically cover everything. Don't worry if you don't fully understand where this formula comes from, okay? You know, it's basically come from, if I divide by the probability of A, it's come from having a think about probability of B given A. So you've zoomed in on A, you still want to be in B, but you're kind of limited to just this bit that has overlap. And that is actually the probability of A and B out of the probability of A. So out of the probability of A, and you multiply up and you get this formula. So anyway, this is telling you to multiply along the branches of a probability tree. And that's what that's telling you to do. So I've got the general formulas in a little box here. These are always true. And then I've got how these formulas change depending on some special case scenarios, right? So these are only sometimes true. It would depend. So if A and B are exhaustive, then this P, A or B formula is like way easier. It's like so easy because it's just P, A or B equals 1. It's like one of the easiest formulas you'll ever learn. But you need to remember it. You need to remember what it means. You need to remember that it goes with the word exhaustive. Right, for mutually exclusive events, then the AND formula becomes pretty easy. It's just 0, right? They just can't happen at the same time. It's impossible. How it affects the OR formula is, well, because of this part is 0, and so you're just adding up the individual probabilities. And what this is telling you to do is add up the probabilities at the end going down in a probability tree, because it's that or that or that or that or that, and they're all mutually exclusive because they're all different paths, and therefore that's what this formula tells you to do, and it's what you've been doing since GCSE. And then, okay, for independent events, the probability, the AND formula, the probability of A and B, this thing here simplifies. Now, it doesn't simplify as nicely as if we're mutually exclusive, right? It doesn't vanish to 0, but it simplifies to just be the probability of A times the probability of B. And that's because this B given A, B doesn't care that A has happened if we're independent, and therefore the probability of B given A is just the probability of B, which I kind of put a little summary here. Now, these ideas, in fact, a lot of the stuff to do with conditional probability, you don't really need to use until year 13. Which is why I'm kind of going to grey it out and possibly recommend to you that you just learn this for the time being. Because at the moment, you'll only ever really have to use this within the context of a tree diagram where you'd already know to like put your probabilities on and multiply across. And this is the only thing you need to know about independent events, this formula here. So this is for year 12. In year 13, you are going to need to know this bit extra and be able to answer questions to do with this within the context of Venn diagrams. So, last thing before I tell you what work I'd like you to do. These 3 things are all what are called equivalences. So what that means is it's not just I tell you that A and B are exhaustive, and then therefore you can tell me that the probability of A or B is 1. It's also the other way around. It's that if the probability of A or B is 1, and I've got to be very careful how I say that, right? Because it's the probability of A or B is 1, then that would mean that A and B are exhaustive. And if the probability of A and B is 0, then that actually tells you that they are mutually exclusive events. So the implication is in both directions. Where that is most often relevant to a question is you will show one way or another that the probability of A and B is actually the product of the probability of A with the probability of B. And from that fact, you will then be able to conclude that A and B are independent. So if probability of A and B is equal to probability of A times probability of B, if this formula is true, then A and B are independent. And that would mean that in the real life situation, A does not affect B and B does not affect A. Okay, the implication is in both directions. Very, very important to learn that and remember that. So, what do I want you to do? Well, I guess first you've just watched a really long video, so you might want to go and make a drink. Might want to have a little rest. But once you're feeling up to it, I want you to go to page 264. So one thing I haven't pointed out yet is this little dash next to an event. Means the oh gosh, what's the word again? Oh, I've actually forgotten what the word is. The complement, I believe it is. Yeah, I believe so. I believe it is. Anyway, you still got the screen on. You can be having a look. You can be getting your book out, right, while I'm doing this. Pretty sure it is. Right, well, in the book they just say not A, but I'm pretty sure that's called the complement of A. So anyway, we'll go with that. So I want you to read page 264, 265. I want you to skip page 266 because I want to discuss probability distributions with you either in a separate video or face-to-face. And then I want you to do question 1, 2, 3, 4, 5, and 6, and 7 from exercise 10.1a. Don't worry about this part here that says write down the probability distribution of x. It is just you drawing this two-way table showing all the possible outcomes, and then from that writing down for each outcome. Okay, you group them together and you tell me and you write down what the probability for each outcome is. Okay, so one simple way of thinking about a probability distribution is you just write down all the outcomes that can happen and you write down the probabilities. That's it. So don't let that throw you off. Okay, we'll talk about that in more detail another time, but it shouldn't stop you from being able to answer question 7b from this exercise. And then I'd also like you to do exercise 10.1b, and you can skip question 2 and question 3 for now. Right, how long's the video been? Oh, it's not actually been as bad as I thought, actually. It's not been as bad as I thought. I thought it was much longer than that. Anyway, hope this has been useful. Any questions, get in touch, and yeah, see you soon. Bye.